Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. This is the fourth video in my Tesla Battery Investor Day series. Today, we'll discuss the battery production line that will help propel Tesla to 2 terawatt hours of battery production in the next 10 years. But before we begin, if you enjoy this video, be sure to like and subscribe. This is the biggest thing you can do to support the channel. I also have a Patreon, Twitter, and have started a Reddit page to discuss batteries. The details of those are in the description. To kick off, let's cover why I think 2 terawatt hours is a good target for 2030. Elon has stated that Tesla will grow by 50% a year. He's also stated that they are targeting 1 to 2 terawatt hours per year of production, but he didn't say by when. At the end of 2019, Tesla was producing and consuming batteries at an annualized rate of around 26 gigawatt hours. If Tesla grows 50% a year for the next 10 years, that puts them at 2 terawatt hours per year at year ending 2030. This gels with both of Elon's statements. Let's put 2 terawatt hours of batteries into perspective. I've calculated a reasonable pack size for each vehicle type in the US, such as sedan, truck, and semi. I then referenced that against the market share of each of those vehicles and came up with a 90 kilowatt hour average pack size. This means that with 2 terawatt hours of battery production, Tesla could manufacture 22 million vehicles a year. That begs the question, how many vehicles are produced a year? There are currently 100 million vehicles produced globally each year, and that's expected to grow 2% a year throughout the 2020s. By 2030, that would mean close to 122 million vehicles a year, and based on other estimates I've seen, that could be grossly undershooting it. Using our 90 kilowatt hour average pack size from earlier, 122 million vehicles would consume 11 terawatt hours of batteries per year. However, what about Tesla's energy storage business? Elon has said that the energy storage business will eventually be the same size or larger than the electric vehicle business. I ran the numbers on a 50% annual growth rate for storage, and this is what I came up with. It's far behind the auto business in terms of scaling and doesn't seem as compelling. However, let's take a look at potential global total addressable market. Globally, more than 25,600 terawatt hours of electricity are generated each year. By 2030, assuming a 3% growth rate each year, that would mean 35,000 terawatt hours per year. How much energy storage backup would that need? It completely depends on the energy generation mix of each country or area. But I'd say 2 hours of storage would provide a nice buffer. I've seen other estimates up to 6 hours, but we'll play on the conservative side. That little 2-hour energy buffer for the world's 35,000 terawatt hour yearly usage would mean 8 terawatt hours of energy storage. That buffer would need to grow over time as the world shifts towards greater dependence on renewable energy, such as wind and solar, that produce energy supply fluctuations. This would quickly push the amount of energy storage needed past 8 terawatt hours, and this would make Tesla's energy business bigger than its electric vehicle business, just as Elon stated. If we add the 11 terawatt hours for vehicles and the 8 terawatt hours for energy storage, that would mean 19 terawatt hours of total addressable market in 2030. One of these numbers, of course, is a yearly requirement, and the other is a total requirement. However, the point remains. Clearly, 2 terawatt hours is only scratching the surface. Elon has stated that Tesla intends to scale rapidly and remain profitable from here forward, with few exceptions. It should be clear why. As we've seen in the last year, profitability provides a halo effect for Tesla and helps tamp down on criticism of the company. I see 2 paths that would be profitable and highly scalable: vertical integration and licensing. Tesla is already highly vertically integrated, so that's nothing new. However, they haven't been fully vertically integrated in the most critical component of their business: Tesla has always had Panasonic as a middleman for battery manufacturing. If Tesla decided to manufacture their own batteries, it would mean bigger profit margins, a greater ability to innovate, and freedom to scale at will. Licensing also seems like an excellent way to monetize Tesla's new battery cells rapidly and at a high profit. However, I'm skeptical. In order for Tesla to license the technology, they need to develop their own pilot line first and work out the kinks before they could sell it as a product. Even after they've fully developed the production line, it may not make sense to send their engineers off to other companies to help implement the technology. One does not simply hand over a blueprint for an advanced battery manufacturing line. Tesla would need to send equipment and engineers as part of the deal. Furthermore, most other companies move much more slowly than Tesla. Why send your engineers off to companies that are slower moving? If Tesla can scale batteries faster on their own than with partners, that's what they'll do. The exception would be if Tesla's cell lines were ridiculously productive. In other words, if they had a surplus of machinery or batteries, then it might make sense to license their production equipment or sell their surplus batteries. With that said, I'd love to see VW and Tesla partner, regardless of whether that's for batteries or something else. VW's CEO, Dr. Herbert Diess, and Elon Musk seem to have a blossoming bromance, and the partnership would make sense. VW Group is nearly tied for first as the world's largest automaker, and Dr. Diess is keen on electrification. VW Group has some of the best engineers in the world, and Elon taps into any engineering talent that he can. Strategically, Tesla making their own battery line makes sense. However, is there any hard evidence of this? Yes, but with varying levels of credibility. These include statements by Tesla where you could read between the lines, supposed leaks by former employees, and the acquisition of Maxwell and High-Bar technologies. Some would say these two purchases make it inevitable, and I tend to agree, but that doesn't make it absolute. Maxwell and High-Bar cover just two parts of a much larger process. These rumors are all we know for now, and it leaves us hungry for the juicy details about the actual production line and what it will be able to do. It's kind of like Christmas. Let's shake the box and see if we can work out what's inside. To make an educated guess, we'll have to take a deeper look at what a battery manufacturing process involves. Here's a simplified diagram of what the process looks like for a typical battery production process. We'll need to walk through the diagram and understand the steps because I expect Tesla will make some big changes. Before we begin, I'd like to emphasize this is a simplified version. If you'd like an in-depth and highly detailed look, I've linked the full process in the description. This was forwarded to me by the mysterious and authoritative JPR007 from Twitter. If you aren't following him, do so. Starting with the left panel, raw materials come into the factory to be mixed. This includes the active materials of the electrodes, additives, solvents, and binders. All this is mixed together to make what's called a wet slurry. The wet slurry is applied to electrode foils in a process called coating. That coating then needs to be dried because it still contains the liquid solvent. That liquid solvent is a chemical called NMP, which is as toxic as chloroform and as flammable as diesel. NMP is evaporated by running the electrode foils through a vacuum oven to evaporate. These vacuum ovens are absolutely massive. The length I found online range anywhere from 20 feet to 180 feet long. The longer the line, the better, because you can fit more product in a larger vacuum oven and increase the speed of the line. Adding further complication, the NMP fumes need to be recaptured because they are too toxic to be released into the environment. All in all, NMP causes huge headaches in terms of cost, safety, floor space, and time. And as mentioned in the technical deep dive video, it has a negative effect on battery life. But it was the best we had up until now. After drying comes calendaring, which basically means flattening and compressing the electrode material so it has the right surface shape and density. And finally, the electrode foils are sliced into the right shape, and this completes the electrode production process. Earlier, we mentioned that Tesla purchased a company called Maxwell Technologies. They have a dry electrode process that will replace this wet slurry process. Let's take a closer look. Maxwell's dry battery electrode process also starts with mixing, but there is no solvent added. The mix includes battery active materials and a binder made of carbon and polymer. The carbon and polymer forms a bubblegum type consistency as it is squeezed through an extrusion machine. Extrusion in this case just means the material is forced through a thin but wide opening to form an extruded sheet. The sheet looks like black wax paper. Finally, that wax paper looking sheet is pressed onto the electrode foils with heated rollers. The extrusion and heated rollers also serve to calender or flatten the material, which eliminates a step. This is all done in one smooth action by one machine. This machine takes up 1/16 the floor space of the wet slurry and drying process, something like 6 feet instead of 100 feet or more that we mentioned above. As you can imagine, the process is much faster, requires no vacuum oven the size of a small building, and requires no toxic and flammable material handling. The middle panel, battery cell production, starts by rolling up the electrodes we've just sliced so they can fit in the tube-shaped battery cell. Then, battery terminal tabs are welded to the electrode for positive and negative connections, and the finished roll is inserted into the battery cell. The next step is filling the battery cell with electrolyte. This sounds straightforward, but the electrode roll is tightly packed into the cell, obstructing the electrolyte from being distributed evenly. This makes filling at high speed for millions of cells difficult. Again, Tesla has made an acquisition here that not only provides them with the equipment to do the electrolyte dosing and injection, but potentially accelerate the process. That acquisition was High Bar Systems Limited, who specialize in the high-speed dosing, dispensing, and vacuum filling of electrolyte solutions into battery cells. I think there was an underappreciation of why Tesla made this acquisition, and many people didn't understand its connection to Maxwell. Once you speed up the electrode production with Maxwell's process, the rest of the battery manufacturing line needs to speed up to keep up. Electrolyte filling was probably one of the biggest bottlenecks on the production line. Moving along, the next steps are to add a seal and a safety vent to the top of the battery, cap it off, charge it, and test it. Charging the battery creates a chemical reaction inside the battery to activate the electrolyte additives. This is called formation because the additive is forming a protective layer on the electrodes. Finally, the right third of this process, battery module and pack integration, Tesla is already responsible for. The first step in the process is module assembly, where the battery cells are packed together in groups of several hundred and individually soldered to connectors. The reason these modules exist is because when Tesla first started making battery packs, their manufacturing was lower quality. Because of that, they needed an easy way to remove part of the battery pack for replacement. However, Tesla has since improved their battery manufacturing and no longer needs these modules. The modules are then tested and joined together in the battery pack assembly, at which point the entire battery pack is tested. We now have a finished battery pack. If Tesla had control over the entire manufacturing process, what would the production process look like? Returning to our battery chart, we can immediately cross off several of the processes thanks to Maxwell's dry electrode tech. Taking a look at the panel on the far right, there is a huge opportunity here. Tesla could upgrade to what's called cell-to-pack technology, which is exactly what it sounds like. The battery modules are eliminated, and the cells are placed directly into the pack. In my view, there are two paths Tesla could take for cell-to-pack technology. First, Tesla could continue making individual cells as they do now, and then place them directly into the pack. It's the next logical evolution to reduce excess pack weight, cost, complexity, and increase manufacturing speed. This is the low-risk, high-reward path. I'll refer to this as basic cell-to-pack. The second path would be very high risk and very high reward. It would be one of the more difficult undertakings Tesla has attempted, and it might not be currently feasible. With the entire production process in their hands, Tesla could fuse together the battery cell production with battery module and pack integration. This would involve a complete redesign of the battery pack itself and a complete rethinking of how battery packs are manufactured. This path would greatly increase margins once scaled and would future-proof the company against competition. I'll refer to this as advanced cell-to-pack. As Elon has stated many times, the pace of innovation is Tesla's moat. Layering Maxwell tech with advanced cell-to-pack would provide one hell of a moat. Let's dive in and take a deeper look. Last year, Tesla registered a patent for advanced cell-to-pack technology. Instead of individual battery cells, there would be plates with the battery cells already welded in place on the plate. The electrode would be rolled and inserted, electrolyte filled, and the battery topped off with a lid that has the venting, wiring, and capping built in. Tesla's implementation may or may not look like this patent, but it gives an idea of the alien technology Tesla is striving for. Earlier, we noted that battery production was getting so reliable that Tesla was no longer seeing defective modules. However, that's in large part due to testing of the battery cells. If the cells were connected to plates like this, they couldn't be tested separately before going into the pack. In order for this to work, Tesla's battery production line would need an extremely low defect rate. Defect and yield rates were covered in the last video. For the purposes of this video, we only need to know that there is a defect rate, and it's probably in the 10% range. Unless Tesla was able to eliminate defective cells, some of these defective cells would get into the pack using an advanced cell-to-pack design. However, there are 3 ways Tesla could deal with these defective cells. 1. They could put extra cells in to accommodate for the defect rate. If all the cells turned out to work in a pack, they could computer limit the pack to make sure that every customer is getting the same experience. 2. They could use higher yield packs in longer range vehicles. The microprocessor industry does something similar with microchips. Microchips come out of the factory with defects, and the ones with less defects go into higher performance products. Finally, Tesla might be able to increase the yield rate significantly. The more complex the process, the more chances there are for defects. As we see here, after removing and combining steps from the original diagram, roughly 30% of the steps have been eliminated, and we are left with a much more streamlined process. These 3 options aren't mutually exclusive and could all be implemented if Tesla took this path. The benefits of advanced cell-to-pack would be huge and could far outweigh the challenges. How much money could this save? George Bauer from InsideEVs estimated that Tesla could save up to 20% per battery pack by controlling the entire battery production process. This article is linked in the description. This estimate was based on solid evidence except for a 4x production rate increase, which seemed to be a gut feel estimate. If the 4x improvement in production rate is factored out, it would be an 8% decrease at the pack level. If we take the 8% reduction at the pack level and apply it to the $105 per kilowatt-hour battery pack from my Tech Deep Dive video, that brings us to $97 per kilowatt-hour. If George Bauer's 4x speed improvement is even half right and Tesla can double line speed, we'd be looking at more like a 14% decrease, or $90 per kilowatt-hour. What would an evidence-based production rate look like for these lines? A typical wet slurry line for pilot production or R&D is 0.5 to 5 meters per minute. A typical production wet slurry process is 20 to 60 meters per minute of output. I found research by Maxwell and A123 systems that indicate a target of greater than 25 meters per minute at a pilot scale. In short, their pilot line was 5 times the speed of a typical pilot line. and nearly the same production speed as a full-scale wet slurry production system. George Bauer's 4x estimate mentioned above is looking quite doable now. I'm going to target a much lower estimate of 50% increase rather than 400% because this will be Tesla's first battery production line. How many gigawatt hours could a line like this crank out? Tesla currently has 13 lines at Giga Nevada with a nameplate capacity of 35 gigawatt hours per year. This means each line is capable of producing 2.69 gigawatt hours per year. Elon advised in 2018 that he expects a 30 to 40% increase in specific energy at the cell level in the next 2 to 3 years. Let's go with 30% to be conservative. With the same number of cells produced, that would put Tesla at 3.5 gigawatt hours per line per year. As above, if we assume a 50% production rate increase over wet slurry, Tesla would end up with 5.25 gigawatt hours per year per line. If Tesla could produce 5.25 gigawatts with a new production line, what could they do with those batteries? We know that the super high-performance Plaid Model S is coming later this year. The lap times it's achieved on the Nürburgring hints to some pretty spectacular new tech. It's a family sedan, and it was roasting Porsche and Corvette lap times on one of the most difficult racetracks in the world. If Tesla offered a Plaid Model S, I would assume they'd also offer a Plaid Model X, because the vehicles use the same battery packs. By that same logic, we could also assume that the non-performance Model S and X would also eventually get the new battery pack, albeit with fewer battery cells. Even though the technology in the S and X is far ahead of the competition, it seems like old technology compared to the Model 3 and Model Y. This is probably why both vehicles experienced waning demand last year. The Model S and X are produced off the same line at the Fremont, California factory. The total production rate that line is capable of is 90,000 vehicles per year. Let's assume at least half the vehicles would be Plaid mode. That's a run rate of 45,000 Plaid vehicles per year. I expect the pack size would also be a bit larger than the current 100 kilowatt-hour battery. If the pack size were 110 kilowatt-hours per vehicle, this would require nearly 5 gigawatt-hours of batteries per year. This would easily be covered by the 5.25 gigawatt-hour pilot battery production line and leaves us with 0.25 gigawatt-hours to spare. 0.25 gigawatt-hours is 250 megawatt-hours. Tesla Semi is slated to begin production later this year at low volume. The battery in that vehicle is expected to be 1 megawatt hour. Those spare 250 megawatts could be used to produce 250 semis. I expect when the first battery production line is finished, Tesla will already be building an improved version 2 manufacturing line. The batteries from this line would then be used to move the standard range Model X and S to the new pack and continue to ramp the Semi. The next lines in 2021 could then be used for Roadster and Cybertruck in any number of combinations. These are all, of course, just educated guesses. What actually matters is the ability to scale. And I have no doubts about Tesla's ability to scale once they've built the first line. As Elon has said in the past, Tesla's ultimate product is their manufacturing ability. I think we should take this statement literally. This manufacturing line will be a product. If a factory is a machine that builds a machine, Tesla is building the machine that builds the machine that builds the machine. In other words, Tesla will mass produce these battery lines. The biggest limiting factor that I expect Tesla to run into is having enough great engineers. This sounds minor, but it's a huge issue. Giga Nevada was having difficulty scaling last year because Panasonic couldn't find enough engineers. They ended up recruiting engineers from other fields and trained them. This is why you see Elon Musk constantly beating the drum for people to work at his companies and running special events to find the right people. There just aren't enough engineers out there, let alone great engineers. In summary, Tesla's mission statement is to accelerate the world's transition to sustainable energy. My best guess is that at Battery Investor Day, Elon Musk will unveil the machine that will make that mission a reality. That is, a greatly simplified battery production system designed for rapid replication that will produce a new generation of low-cost, high-density battery packs. This is how Tesla will get to 2 terawatt-hours of battery production a year by 2030, and potentially more if Tesla continues expanding its partnership with Panasonic or establishes new partnerships. Breaking news. As I was finishing up the recording for this video, Shirley Meng seemed to confirm that the technology she has been working on will go into future Tesla battery production. Philip is a friend of the channel. Nice work, Philip. If you don't know who Shirley Meng is and her connection to Tesla and Maxwell, see the video above or linked in the description. In the next video, I'll be updating the information from the technical deep dive video. If you enjoyed the technical deep dive video, you won't want to miss it. A special thanks to Brad Ferguson for your generous support of the channel and all the other patrons listed in the credits. I appreciate all of your support and thanks for tuning in.